We're still looking at special right triangles today, but this time with word problems. So we have the added challenge of having to create our own diagram instead of being provided the diagram up front. That means we have to think carefully about any vocabulary that shows up in the story problems and how that creates the picture that we're trying to draw. And we'll talk about some techniques along the way, but let's look at these three examples. All right, so example number 1, you make a guitar pick that resembles an equilateral triangle. All right, so there's some vocabulary that will help guide us in our picture with side lengths of 32 millimeters. And the question is, what is the approximate height? So approximate means we want a decimal value, even though typically with special right triangles we only want the exact value. We'll still use that as an answer. Because it's a story problem, occasionally we'll dip into decimal values for answers. Let's start off with the equilateral triangle. You know that means that we have a triangle where all the sides are equal in size. So that's where we start off by drawing a diagram. And each of these are 32 millimeters. mm for millimeters. Okay, they're all 32 millimeters, and we want to know what kind of special right triangle it is. You know, with the special right triangle, you either have a 45-45-90 or a 30-60-90. In other words, you're focusing on the angles, and we don't have any information about the angles. And that's part of the challenge here. So let's think about this. We've learned in the past that if a polygon is equilateral, then it is also equiangular. So it turns out these three angles will be the same size. All right, so that's a step in the right direction. What that means then is that all three angles in the triangle have to add up to 180 degrees. So if you take the total and divide it into three equal-sized angles, that means each angle will be 60 degrees apiece. All right, so that's a step in the right direction because now we have information on the angles, but that's still not a special right triangle, is it? We're looking for either a 45-45-90, which is not this one because we don't have 45s, or it's a 30-60-90. And hey, there's a 60. We got lots of 60s, but where's the 30 and where is the 90? So this is where we then have to bring in the height, right? We know the height is perpendicular to the base. There's your height. It does, after all, say what is the height, and that's what we have to find. And notice by drawing the height, it splits the large triangle into halves. We have two congruent halves. So now we're going to draw again half of the triangle because this is our right triangle. So there's your right angle. There's the 60-degree angle. And up here at the top, that's not 60 anymore because we cut it in half. We've bisected that angle, so that means it's 30 degrees on either side. So this is a 30-degree angle. So this step of the process here, we're going to label the sides of the special right triangle. Right, so in other words, we had learned about once you identify your smallest angle, right, you know opposite the smallest angle is the smallest side, so there's your short leg. Opposite the right angle is the hypotenuse. And then the height is in fact your long leg. And let me put the H on there so we know that's the height we're solving for. Okay. Now that we have our special right triangle, we can solve the problem. More specifically, we're going to find the height. All right. The height is on the long leg, so we want the formula with the long leg. Long leg equals short leg times √3. There we go. And the short leg is unknown. Well, it's not unknown. We just don't have that information yet because I didn't draw that from the picture. We know this hypotenuse is 32. And we know the short leg is half the length of the hypotenuse. So we can either cut this in half, or you could take the base of the original drawing and cut that base in half, and that would give you 16 millimeters on either side. So either way, you can cut the base in half, or you can take half of the hypotenuse, because that's also something that we know. There we go. There's the short leg. So the long leg is the height that is equal to 16 root 3. And that's the exact answer in millimeters, but because it wants the approximate answers, we'll go ahead and type that into our calculator to get a decimal value. And again, we're going to 2 decimal places. So those are the answers, exact and approximate, both. Here's another situation. All right, here we have a right triangle that's going to be represented by these windshield wipers. A car is turned off while the windshield wipers are moving. So if you've ever seen that happen, the windshield wipers kind of freeze in place. The 24-inch wipers stop, they freeze in place, making a 60-degree angle with the bottom of the windshield, right? So I'm underlining these things because these are going to help us construct our triangle. The question is, how far from the bottom of the windshield are the ends of the wipers? All right. So think of this as the bottom of the windshield. So pretend you're sitting in the driver's seat looking out. And this is the bottom of the windshield. You can kind of think of like a big rectangular region of space representing the windshield itself. But this is the bottom of the windshield. And you have these 2 pivot points where those windshield wipers are going to go back and forth, okay? We'll just take a look at one of them to represent our triangle. So you have this wiper, it's going back and forth, and at some point it freezes. It stops. How did it stop? It says that it makes a 60-degree angle with the bottom. So this is the bottom. It is rotating upwards until you get 60 degrees, and then it stops. And there's the end of the windshield. All right. So this is the 24-inch wiper. And what I meant to say was this is the end of the wiper, not the end of the windshield. All right, so there's the wiper, 24 inches. It goes back and forth like this. It stops right there. This is the end of the wiper. So what we're doing is part of not just creating the triangle, but taking some of the vocabulary in the story problem and labeling it. You can see here it says, how far are the bottom of the windshields? How far from the bottom of the windshields are the ends of the wipers? Right there, that is the end of the wiper. And this is the other end, which is literally on the windshield wiper here. So that's the other end. All right, so the question is, how far are the ends, those are the 2 ends, from the bottom of the windshield, right? So this is your bottom of the windshield. Now, obviously it takes longer to label all of these parts, but this is a technique to use to help keep track of what the phrase in the story problem is calling these items, so that when it asks you to find a particular item, you have a bit more information to go on. We obviously want to turn this into a triangle here, and we will in a moment, but those are some of the crucial steps that you want to consider, and we'll see that again in example 3 here in just a moment, where you're just taking a moment and identifying the phrasing used in the question or the phrasing used in describing the item to help you identify what information you have and what information you need to find still. Now when it says how far from the bottom of the windshield are the ends, we don't mean this distance. That's not what we're talking about, because when you're talking about from this distance to the bottom of that windshield, you want the shortest possible distance, and the shortest possible distance is a direct path that leads you in a perpendicular connection to that bottom of the windshield. That's our right triangle. So if this is 60 degrees and that's 90 degrees, this must be 30 degrees. So now we know this bottom of the triangle is our short leg. It's opposite the 30-degree angle. The 24 inches is on our hypotenuse. And the height is the long leg. So turns out that when it says how far from the bottom of the windshield is it to the ends, they're really just asking for the height. It's the exact same thing as saying find the height. So once again, we want to find the long leg. But the long leg is based on the short leg, and I don't have the short leg, right? So you have to start off with your hypotenuse equals 2 times the short leg. Your hypotenuse is the 24 inches, and that means your short leg will be 12 inches. So now we know this is 12 inches. Then we can go to the long leg equals short leg times root 3. The long leg is the height, but I'll just call it long leg. And the short leg is now 12. So 12 root 3 inches is the precise distance, which is the height of that triangle. They're not asking for a decimal answer, so we'll stop right there. That's its length. Here is the third and final example in this section. There's a bit more detail here. So again, you're going to see me using the same technique where I'm labeling parts of the diagram. And we're going to start off with flying a kite. All right, and you had let out all 50 feet of string when flying your kite, but now it's stuck at the top of a tree. So do you see that? Top of a tree? That's going to be a location that we want to keep track of. Right? So we got 50 feet of string. Now stuck at the top of the tree. The string makes a 30-degree angle with what? With the ground. So we have to label the ground. So here's my ground. Label it. Here's the tree. Label it. And also label these other phrases we came across, like the top of a tree, so top of tree, and bottom of tree. It will help you keep track of the information as we get to understanding what it is they're asking us to solve for. Now, you are also part of this, you. So where are you standing? Not at the tree, probably some distance away. Now we have to make a triangle out of this, so we're not going to put the string in our hands. We're going to pretend that the string is completely on the ground. So there's the string. And we were told that's 50 feet of string, connecting you with the top of the tree. And there's your kite, stuck in the top of the tree. We'll assume the tree is at a right angle with the ground. All right, so that's what I mean by diagramming. When you're diagramming, you're trying to be pretty specific with locations, like where are you? I'll put that on there. Where's the tree? Where's the top of the tree? Where's the bottom of the tree? So the first question they're asking is, how tall is the tree? So that's pretty clear. We know what that is. But notice the second question. How far are you from what? The base of the tree. So when you see that word base, that's another word for bottom. So in other words, it's not saying how far are you from the top of the tree. It's saying how far are you to the bottom of the tree. That's this side here. So we're really finding both sides. We also have this 30-degree angle with the ground. So the string and the ground are where the 30-degree angle belongs. So here's the string, here's the ground, and where the string and the ground meet, that's our 30-degree angle right there. So if that's 30 degrees, that's 90 degrees, that has to be 60 degrees. So now opposite the shortest angle, smallest angle is the shortest side, so that's our short leg. The ground is the long leg. And of course the string is our hypotenuse. We have everything labeled. The first question is, how tall is the tree? I'll call that H for height. It's also the height of the triangle. And so that's the short leg. So long leg equals short leg times root 3 is one of our formulas. And the other one is hypotenuse equals 2 times the short leg. Of course, we have information on the hypotenuse, so we'll start with this one. So 50 feet of string, divide away the 2, and that means our short leg is 25. So now we know the height of the tree is 25 feet. Take that information to the next, and the long leg is 25 times root 3. That's also in feet, right? And that's answering the second question. That's how far are you from the base of the tree? So there's our two results. There's that second question, and there's that first question.